Hi, I'm Naru Sundar. I'm a principal engineer at Intel and run software architecture for our network and edge connectivity group. I work on IPUs and NICs and a lot of networking topics in general, both on the software and hardware side. And I'm here to talk to you today about networking for AI and fabrics for AI. So to get started, it's always good to step back and realize the fascinating moment in time that we find ourselves in. The techniques that underpin large language models like ChatGPT, like Bard, and all the new up-and-comers have been around for a long time. Some of those theories date back to the 50s. What's occurred in the last few years is that we've crossed a threshold. It's a threshold that intersects our ability to aggregate a wide enough and complex enough data set to perform the appropriate computational transformation on that data set fast enough to produce a usable functional model with wide-ranging applications. This requires the conjunctions of technologies that have been maturing through the last couple of revolutions we've had, the mobile revolution, the cloud revolution. These are technologies like heterogeneous compute, networking technology, memory technology, storage technology, and the massive amount of scale that we've gone through already in trying to create sort of a ubiquitous data sphere with all the applications and services that we can access from our phones today. Now that we've crossed this threshold, we have a new view of what we can achieve with AI-based applications and solutions that we can deliver at human timescales. From smartphone apps that summarize doctor's visits, to modeling tools that optimize engine designs, to strategy generators, to video generators and audio generators. The sky is the limit in the terms of AI-based solutions, and it seems like new opportunities are coming up every day. And what we notice is that the training time to train these large models is doubling every 12 months. And that training time is driving the evolution of the modern data center. It's driving everything from the memory bandwidth cutting edge to the SerDes nodes that connects elements in the data center. It drives how fast compute goes, how fast GPU design needs to grow. With every scale threshold that we cross, we increase the fidelity of these models. As the fidelity grows, we create new applications, we create new solutions, and this in turn creates new rise for being able to deploy inferencing on these models so that we can access results from these from your smartphone, from retail stores, from industrial sites, from the cloud, and beyond. So if we look at how we sort of get through there from a networking lens, most folks tend to start development with small single node elements where they're prototyping some sort of model. Maybe this is a small targeted model. Maybe it's a model that's feeding input to a cloud data center. Maybe it's it's sort of massaging data to feed into a large model later. And at some point, they have to grow that. And this is when you start going from a single node solution that you can buy off the shelf to having to figure out, how do I build that into a cluster? Whether it's 5,000 nodes or 8,000 nodes, whether you're building that inside an on-premise infrastructure, or you're building that in some edge location, or you're leasing that out of the cloud, that you've gone sort of from one modality to now having to figure out, how do I build these sort of distributed solutions? And then you start looking at, okay, now I've got my model, now I need to scale it, now I need to feed in more training data. And now when you're looking at LLM scale models, you're looking at 10K nodes, 32K nodes, 64K nodes. Because training time matters. The bigger the cluster, the faster I train. The faster I train, the faster I can get turnaround for my application that runs on these models, right? So because these models are fundamentally defined by how accurate is the data that we feed in, and every time you generate new data, you put it out, you put ChatGPT out there and let everyone type in what they want, and that's feeding more data into it. And there's a process for taking that data, updating the model, retraining that model, tweaking it so that you can add new APIs. Maybe you've gone from language recognition to image recognition. All of these require retraining. The faster you're retraining, the faster you can get to a solution that you can sell. And the dynamics of doing that retraining at scale and being able to deliver that matter, right? And this is why we start talking about clusters, because it's one thing to figure out how do I take a bunch of GPUs and a platform and put them together. It's another thing to say, okay, how do I get a whole bunch of these to work together? How do I orchestrate that? How do I make sure I have the right storage to not bottleneck that? How do I make sure my network isn't a bottleneck? How do I make sure that if there's an issue, I can figure out where the issue is? Because debugging large-scale system problems at these kind of cluster sizes is hard. It requires a lot of telemetry acquisition. It requires a very deep understanding of the dynamics of data flow through these nodes, and it's not easy. And that's why there's many vendors who are trying to define cluster-level solutions, because if you can engineer at a cluster level, then you can create something predictable for your customers. The last thing you want is your customer to run into an issue and they're not able to make progress in their model. So we're going to spend a bunch of our time today talking about the topology that is the reference platform for the biggest clusters. Now, this isn't to say that there aren't other topologies, but I think it's from our lens, if you can understand this topology and understand the dynamics that are at play here, then it's easier to go down from there. Whereas the modalities and the nuances going up it doesn't work in the other direction. So you want to look at this picture as this is my 64K cluster node or 128K cluster node that maybe it's in a hyperscale data center. Maybe I've just built out a big one in some my enterprise data center. So these systems, you have to understand, their purpose is to do large-scale distributed computation, right? At the end of the day, that is what underpins all of most machine learning models is I have some state, I have a large amount of data that goes in, I update my state, rinse and repeat, and you cycle through updating things over time. Large distributed computations at these scales requires lots of GPUs to do the number crunching. It requires networks to be able to merge and massage data together. So at the heart of these fabrics is you have some form of AI accelerator node. This is the orange box here in this picture. This node has a couple different elements, and we're going to talk through each of those pieces. So this node, as shown here, obviously has a bunch of GPUs. This is not the only way that you can do machine learning today. You can do machine learning on CPUs. It's a question of what is my power cost trade-off, right? Tensor operations per second. That's the benchmark that we use, right? If I can live with slower tops, I can have cheaper CPU-based solutions. If my training time is dominant, I need to go to the cutting edge on the GPU side, and it's a design choice. So here we have some GPUs. These GPUs are not sitting there in isolation. They are managed by some CPUs that are local to the box, and they are connected together in two different ways. They're connected within the box with what we call a scale-up network. This is an interconnect that sits between the GPUs within that accelerator platform. And they're connected box to box through what we call the scale-out network. And we'll talk through each of these two networks and what their role is. Additionally, you see here that there is an IPU, infrastructure processing unit, sometimes also called the DPU, that is in the box. And then to connect the GPUs to the scale-out network, there's a NIC. Now, you might also see in some pictures that these, instead of a NIC, you might see a DPU there as well. But there's some form of network connect between the GPU to get data out into the backend side. So, and then this cluster sits connected to the standard Ethernet data center network. This might be your cloud operators network. This might be your enterprise network. It has a bunch of other services on it. It has a storage fabric. It might have other networking services, firewalls, load balancers. It has access to the external world. So typically, especially in the cloud hyperscale case, the way that standard Ethernet data center network services, the storage, other virtual instances, other network services, they're all abstracted through an infrastructure processing device. So from the point of view of those CPUs, which are the things that are actually running your machine learning applications, they might see a virtual network device, they might see a virtual disk, and all of that is provided through the abstraction that the CSP provides in the IPU. Now, that is your data ingest. That's where data comes in for your training data. Maybe it's coming in from the outside world. Maybe it's sitting there stored on some storage fabric, and you want to bring that in. So that's your access to networking, storage fabric, and anything else the CSP is providing. And then the scale-up network is your GPU to GPU fabric, and we'll talk through the characteristics of that fabric. And that allows, when the distributed computations happen, that allows those GPUs to communicate data between them. And there are different modalities in which they do that for different types of workloads, and we'll talk about why that's important. And then sometimes we need to take that data, we need to ship it out. So these GPUs are connected through NICs into a scale-out network that's distinct from the standard Ethernet data center network. There are use cases where they may be using a common network, but typically for training clusters, because these things are leased, you want to have predictable networking on the back end. And you can't have predictable networking, as much predictable networking in the standard Ethernet data center network. Typically, you have a single tenant on these CPUs because sharing multiple AI machine workloads on the same box is very challenging. It's easier to lease them at a node level and lease n nodes together. That's a single tenant's application. So we're going to talk through each of these and talk through why, what their use is, why that's important. So let's talk about the front-end network. So again, we have IPUs and DPUs here. Now, this doesn't have to be a hyperscale CSP. It doesn't have to be an AWS, Azure, Google Cloud type deployment. This could be inside your own data center. But there's still a need to have an infrastructure device there. And that's because you still need a place to land the orchestration and management of the box. Because typically, you want what customers most want is they want to use those CPUs for their machine learning function. They won't have to deal with the system manager or the storage manager, the GPU manager. You want to push that down into an abstraction so that you have all that CPU available just for doing the coordination. So if you're trying to think about an engineered solution at a cluster level, that IPU in an enterprise case can be a great place to land that type of orchestration. When you're in a CSP environment, that is where the CSP's infrastructure stack lives. Now, this CSP infrastructure stack can be doing a large amount of the provisioning of the system. It has to provision the data plane on those NICs so they can talk to the backend network appropriately. This is, IP addressing, routing, things like that. It has to do all that configuration because that's not something that the tenant wants to manage. There is provisioning and managing of the GPUs and the GPU memory, bringing them up, spinning them down, doing any sort of debug, telemetry, finding out when when things go wrong. That kind of work has to happen on that IPU. And then any sort of other resiliency or like, hey, I've got an issue on my scale-out network and I want to do some debugging. That's a great place to drop that kind of function on there. Because again, you want to keep that separate from the actual ML workload that's running on the CPU. In most of these distributed applications, it's a combo, right? There's sort of a coordinator function that runs on the CPU and it's loading, bits of code that run in the GPU that do the distributed operation. And so that CPU plays an important role in sort of organizing and going through the phases of the ML function. And so again, can this be put together individually in parts? Yes, if you have the right software and you have the right standards behind it. And that's one of the things that we're going to start talking about, which is, where does this kind of system start relying on proprietary elements that make it harder to kind of building block this whole thing together? So the scale-up network is the next interesting bit here. So again, this is your GPU to GPU communication fabric. And because so much of the ML processing function is distributed in nature, the available bandwidth and the structure and the latency of the system and its semantics is really important. Many ML operations are hierarchical in nature. I split up my work into a bunch of different nodes, and I have to aggregate them in some hierarchical way, right, to make it easy to merge that data. And when you're doing that kind of hierarchical merge, having lots of bandwidth down at the leaves of the tree makes a big difference. Whereas other operations require me to talk GPU to GPU, and I'm just kind of merging it all together. So there is a natural difference in the amount of bandwidth I need down within these boxes versus the backend. And in fact, if you look at reference designs today from NVIDIA and AMD and Intel Gaudi, there's a much higher ratio. So in the current gen NVIDIA and AMD designs, it's about 9-to-1 available bandwidth on the backend side versus on the scale-up side versus the scale-out side. And that's significant given that most of these scale-out networks are running today at 400 gig. That's 9 times that bandwidth available on the backend side. And that drives a lot of performance. At the end of the day, the reason you have this is because it's performance. If I have a network bottleneck, and you think about those phases of do computation, aggregate, transform, compute, rinse and repeat, if one of those steps has a bottleneck because of the congestion or the amount of bandwidth available, you've slowed down your entire train, right? And when you think if you're an end customer and you're leasing this GPU cluster, it's dollars on the table, right? A lot of these platforms have about 8 GPUs within a node. There's a cost power trade-off function, right? How much can I fit in there? What do I need for this backend fabric? Do I need switches? Do I need traces? Can I cool this in some reasonable way? How much power can I deliver to a single box? All of these are trade-off decisions, and it seems like we've kind of hit a sweet spot right now, whether it's about 8 per platform. And these platforms are very large in power. It could be tens of kilowatts, right? Which makes a big difference in terms of how you construct your rack. We've talked to CSPs where, used to be they had a 24 kilowatt rack and they could put 24 servers in a rack, and then they stick one of these boxes in there, and now they're like, we're trying to, do a lot of rebalancing here. Power is a big factor, right? Power delivery, as much as the compute capacity has grown, the available power capacity is not growing as fast, right?
That's very much a problem I deal with on a day-to-day basis. Lindsay Hill, by the way. We have all these racks that used to fill full of servers, and now maybe they're half or a third full, and I'll have gaps between a lot of my servers as well, partly just to improve the airflow. Partly because the higher, the faster optics, so the 100 gig optics and things, they run hot.
Everything,
and you get a little bit hot at the back of the cabinet, and it's really frustrating. I've got all the space and these data centers.
No wonder that immersion cooling was one of the hot topics at OCP this year. Right?
Yeah, I can't get the power in this.
Yeah. Power delivery is going to be one of the tension points in the system, right? We are, if you look at the process dynamics, right, as these systems grow gen on gen, right, we're paying for the increased compute capacity with increased power, and at some point we have to manage that, right? Process gives us somewhat, but we also need to handle this doubling of the models, right? So this is a data center dynamics problem, right? Everyone knows that the demand is there, but
I don't see it getting better in a hurry.
No, because I mean, a data center build out is somewhere between like 3 and 5 year lifetime, and you pick your power footprint up front, right? You're not going in later and saying, hey, can I deliver 2x the power? So this is it's an industry challenge, right?
It's an equation, though. It's not like an either or. So there are ways you can balance it out. Can you talk a little bit about, from not from the data center side, but like from the individual boxes side, what sorts of things are done to make the most of the power that's delivered to the server?
Yeah, no, that's a good question, right? There is the power. If you look at the server, and the server has effectively GPU compute, some CPUs, and networking, the GPUs are the biggest consumer of that power, right? From a cost perspective, networking is about 15%. From a power perspective, I think it's similar. It's maybe like 10% or something like that. The GPUs are still the big power driver. Now you could try and pick a different form factor, but I think part of the challenge is that, at least, I'm not a big data center specialist, but in general, power delivery is at the rack level and not at the unit level, right? So it's, you can tweak your rack form, your unit form factor around, but you're still dealing with the limitation of the rack, right? Because that rack was built 2 years ago. So you could try and distribute it more, right, across many racks, right?
I guess in just kind of playing it in my brain that there are two ways you could do it. You can build beefier racks, right, and try and deliver more power, and then you'd have to play this game where you're trying to see into the future and your crystal ball, and you're trying to figure out how much power am I going to need at the, at the very tail end, far out. But the flip side of that equation is that you can look at what you're putting in to the racks and say, on an individual basis, where can I economize how much power I'm using? How do I make how do I become more green? How do I become more efficient, use the limited power that the rack is providing to the best degree? And
so there's certainly, and we come from the networking side, right? So we're not necessarily driving the GPU side of it, but from an industry perspective, there's certainly a drive to be, what we hear from our cloud customers is that the benchmark for performance ought to be double the performance at ISO power. Not double the performance at 2x the power, double the performance at ISO power because of this, right?
So what I'm also hearing you saying is that that because most data centers traditionally have been built around CPU and, in the case of networking, racks of power and heat from optics, and so the cooling comes into play there. But they've been built around traditional CPU.
That's right.
Heat dissipation and power usage. And in the world of AI fabrics, AI in general, the GPUs tend to start pushing those boundaries more so, because a GPU is going to put out and draw more than 3 times the power of a CPU running full out.
It's a different lens. And I think that's one of the reasons, years ago, we've talked with different customers about HPC applications and when HPC went into cloud. And this was sort of the genesis of this conversation, right? And yet sort of ask the question, are you going to build a separate HPC cluster and optimize power and cost and networking around that? Or you can try and just insert HPC capable units in your general data center and try and create an equivalent SLA of a specialized system. And, at the time, it seemed like the providers that were offering sort of exascale systems on a leasing model were going the specialized route. And I think that hasn't really changed because that's probably the easiest way to be able to do specialized power distribution, right? If I have my AI clusters and that's in one part of the data center, I can at least drive power and I can have a 36 kilowatt rack instead of a 24 kilowatt rack and play that game. So that's coming out, there's no free lunch. Right. It's coming out of somewhere. Right.
I mean, it certainly doesn't make sense for most data center architects to build for standard generic processing purposes a high performance cluster, AI GPU intensive or GPU driven environment, because that's going to be a lot of money for what would normally.
This is the dynamics of the system. Do I buy this on-prem and invest in that and deal with the data center architecture in order to support that? Do I lease that, which has a different cost model, right? And do I have data provenance issues with leasing that, which is a third angle on this. We haven't talked about the regulatory sort of side of it, which I'm not going to in this talk, but you could imagine that adds another lens on whether you lease or whether you do on-prem or you do some hybrid. So there's no easy answer, right? And I think what we observe is we're at the uphill side of the training curve, right? Models are getting bigger. We're going up that ramp. But, there's the running joke at OCP was every VC fund that's coming up in the next year has to buzz AI, right? Yeah. These guys are delivering solutions. Well, what are they going to do? They're going to deliver solutions. And those solutions are going to run inferencing on these clouds. So the inferencing curve is running behind it. The growth curve for models is, that doubling time. The inferencing runtime is going to follow the same curve. It's just 3 or 4 orders of magnitude less time. There's the same problem of how do I deploy inference at scale, right? If I want it globally accessible worldwide, right? How do I, am I buying small racks in my industrial layout, or am I buying a retail setup? All those kinds of questions have to be answered, right? So we're still, whether it's inferencing or training, there's still going to be that demand, right? And we're still, at the early stages of trying to figure out how to solve that from a power and cost point of view.
Well, it's not really a question more as much as it's a comment. I think, so Nick Braulio, by the way. This looks a lot to me like the high performance computing model is sort of creeping in to the, more of a mainstream role with, how you're developing these clusters, how, and the, the requirements to, you for power, space, networking,
Yep.
all of those things. All this sounds really familiar to me because in a former life, I did a lot of HPC stuff. And I'm curious what amount of, if any, investigations have you done into how prior HPC systems have been built and how does that relate to what you're seeing going forward here?
It's a good question. We ourselves have lots of folks with HPC background in our teams. They inform a lot of our strategic choices because they've had learnings on this, especially on the networking side, right? The networking for AI fabrics and the networking for exascale HPC systems share a lot of commonality. Some of these GPU vendors themselves are building exascale systems using, these kinds of techniques, right? So but I think I guess the way to put it is the demand for these systems is on a much higher order of magnitude than I think some of the HPC applications. There's lots of interesting HPC applications and xScale systems that run today, but I think it's
but you're right.
type
They're
of
mostly
demand.
Specialized, right? They're meant
Yeah.
to do one particular thing, high energy physics, or
like you don't if your high energy physics run takes
built.
Yeah, if your atomic modeling run takes 3 months to run, that's fine, right? But if you're trying to monetize a large scale LLM model, right, you're on a different metric for how fast things need to train, how fast you need to turn around the next round of data on, right?
Yep.
That's driving a lot of these dynamics. Okay, so just to continue this story, so we talked about the scale-up network. This is GPU to GPU. So equivalently, there's a scale-out network. This is GPU to GPU between boxes. One thing that's important to point out on this one, I didn't get a chance to because we had all that great discussion. The protocols used on this backend, on this scale-up network, it's very important to point out, is proprietary today. So different vendors have different custom implementations. NVIDIA uses NVLink. AMD uses Infinity Fabric. The current generation Gaudis use a custom form of RoCE, which is RDMA over converged Ethernet. The NVLink and Infinity Fabric versions are memory store models, right? So they give you a coherent memory domain within the GPU box. That's not necessarily required. It just is a characteristic that they take advantage of given the genesis of those systems. And so that custom protocol aspect does lend it to play because now you can't intermix GPUs. They use different protocols. That means that when you look at boxes, you have to sort of buy them at a vendor level, at a box level, right? And this has other dynamics that come into play. When we compare to the scale-out network, the scale-out networks also use custom protocols. NVIDIA offers both InfiniBand and a custom RoCE over Ethernet. I say custom because there is a standard RoCE over Ethernet, but historically that version of RoCE, the standard one, has had scaling issues. And there are folks who get it done, but it's very hard to broadly deploy. And we've had customers who basically avoided going down that rabbit hole because it's been so hard. The scale-out network has to handle going to about 64K, 128K nodes. These are the cluster sizes that they're talking about in the top end. They're very deployment specific, and these are switch networks, so there are switches in play. Sometimes these switches themselves are trying to do specialized things like out-of-order delivery or their own.
So I was just wondering about you got custom protocols. What does that mean at the switching fabric layer? Does that...
There's two ways to answer that question, right? Historically, the large cloud providers have wanted their switches to mostly be commodity and mostly be large.
I want to be able to use those. I want to just be the same, my general pool of stock.
And so if you look at the genesis of congestion protocols that are public, most of them are end-to-end. Because the moment you need the switches to do something, now you're talking, okay, do I have that switch? Do I have a way to negotiate which switch is there? But because AI fabrics are a little bit more customized, there's certainly lots of vendor interest from switch providers to see, can I help the problem, right? So we'll talk a little bit about UEC later in this talk, and UEC certainly has participation for the switch vendors. You know, there are Broadcom switches that do reordering, in-switch reorder, right? Now, that's an architectural choice, right? Is that the right long-term choice? Hard to say. So I think it's a place where folks are looking to add value because they're part of the cluster solution and they're looking at ways that, you know, they can differentiate there. But it gets back to, again, you know, if there are custom protocols at play, it makes it harder because then you're again dealing with the vendor lock-in problem, right? Congestion management is a big deal in these set of systems, right? Within that scale-up network, because there's such high bandwidth and it's almost point-to-point, there's not as big of a congestion problem. When you're talking the switch network on the scale-out side, congestion management is a big deal. Having programmable congestion control so that you can tune that and adapt that for different types of workloads is a super hot topic right now. And I think it drives some of the motivations for some of the choices in whether it's a NIC or a DPU on that backend network because folks want to have that kind of control.
Can I jump in for just a second?
Yeah.
Sorry, Remington Moose. You have up there custom Rocky over Ethernet, and there's a question that someone in the channel had dropped out, and I was kind of confused by that as well. Is that accurate? Are you actually saying they're running, because Rocky is RDMA over
standard, but
over
if you
Ethernet.
look,
So are we talking Ethernet on top of Ethernet here?
It is. So there is Ethernet, and there's the Rocky standard as defined by the EBITBDA, and then there's what folks customize on top of that. Historically, the Rocky V2 spec has been targeted at lossless networks, right? Which requires enabling pause, and it's a whole deployment thing. Academics have, you know, as of 5 years ago, we're already proposing different ways to solve that problem. It's never made it into the spec, but it's made its way into vendor-specific implementations, right? And some of these technologies have made their way into UEC. They've made their way into Falcon, which Google put out into OCP that we are supporting on our NICs that have some of these features. But that's one of the challenges in the system is that the Rocky V2 spec as it is has its scaling challenges. Don't get me wrong, there are folks that deploy it, but at smaller scales. It's become harder and harder when you're talking 1,000 nodes, 10,000 nodes. There are big problems with trying to create lossless networks on that space. So we talked to a lot of customers about AI fabrics. They say AI fabrics are too expensive because, you know, these clusters are already expensive, right? And especially when they're custom solutions all across the board, it's expensive. There aren't enough options. There's just one. That's a common refrain we hear. That's the problem with having vendor lock-in is that there's just one solution. People want to be able to building block these systems because, as you can see, there's a lot of cost, power, perf trade-off points. And the more you can build the system out of building blocks, the more you can tune a particular build out to a really specific trade-off profile, which of course means that you need interoperability. So if everyone's using custom protocols, I can't mix and match. And it's too complex. And this is sort of the challenge is that even with, you know, a whole system for one vendor, there's a lot of software and there's a lot of orchestration that goes along with building these solutions. And that interoperability piece is sort of the heart of it, right? Because if we're not all talking the same protocol on the same wire, on the same underlying interconnect, it's hard to get past that. So we're not alone. So as some of you might have heard, the Alra Ethernet consortium was formed last year. It has a lot of initial participating members. Intel is part of that. We're a fully participating member in this. And the goal of UEC is to deliver an Ethernet-based, interoperable, high-performance, full communication stack that meets both AI and HPC at scale. So this is both a wire protocol spec and a stack. And they are working on the wire protocol side now. There's a spec that should close sometime next year. You know, there's no real firm goal right now. And once the spec is closed, you're going to have vendor implementations, and that gets you to a future point in time where you can have a Rocky alternative that is fully sort of up to date in terms of the state of the art, in terms of features of transports and reliability and resiliency, that is multi-vendor supported. And this includes everything from congestion management to how the switches participate in there, to the resiliency of the wire protocol itself against drops and errors and things like that. But UEC there's no UEC implementation today because the spec is still in work. So we at Intel are also trying to move the needle forward. So as some of you may know, our ASIC-based Intel IPU, the E2000, was a co-design with Google. We're selling that to other customers as well, but Google was a partner in that design. It's deployed in Google today. And one of the things we worked on in that ASIC was an implementation of Falcon. Falcon is a Google transport technology that we have in our ASIC silicon. It was publicly announced at OCP, I guess last week. There are a couple of talks on it. You can go find those online. There will be a spec for Falcon from the wire protocol side in the coming year. And we at Intel are working on a public software stack for that will go along with that. So we will support that in our ASIC IPUs today. We'll be supporting it in future ASIC adapters. And Falcon is not a competitor to UEC. It's just it uses some of the same ideas that feature into UEC. We are not wedded to either. UEC will arrive at a certain point in time, but we also have to cover that point between now and then, right? And there might be eventual protocol level alignment between the two, but I think there's no competition there. It's just where there's multiple conversations going on in this space, right? The goal is to get to a multi-vendor interoperable standard, right?
Can you talk just for a second about what you mean when you say state-of-the-art congestion control and what that specifically means in this case?
Okay, so if you look at Rocky V2 and you look at some of the congestion control algorithms that are sort of baked into that, things like timely or DCQCN, one of the reasons they're baked into the spec is that most congestion control algorithms do have a wire format component. If you have congestion signaling, how do you carry that congestion signaling? What is the format of that congestion signaling, right? You can't get away with and say, oh, I'll just throw in any congestion protocol on top of it. And that's part of the problem with this, with how congestion signaling interfaces with the standard. Is because the moment you don't define that, you're going to have vendor interop issues, right? Somebody's going to implement, algorithm A with this format of the packet, and it's going to be incompatible with algorithm B. So the congestion control has to be part of the standard, right? Some mechanism for how you encode that on the wire. So since that time, if you look at the public, there are lots of investigations in congestion control, right? Congestion control is part of the TCP stack. It's part of the Quick stack. It's in the data center stacks that are used in the cloud providers. So there's lots of public work on better congestion control algorithms. Now, what's good for TCP isn't necessarily great for an RDMA protocol on the back end. They have different models, right? So for example, our ASIC silicon has an implementation of Swift, which is a protocol that was it was developed at Google. They opened that protocol. It's available now. Swift was originally designed for UDP-based connections, but has lots of applicability and tuning for handling these kind of RDMA networks. So being able to support more recent algorithms is one need, but being able to swap those around in a way that the protocol will tolerate is an important need, because there's too much churn going on. I expect today's protocol to be dated by the time tomorrow rolls around, right?
Actually,
yeah,
I want to follow up on Remington's question, Micheline Murphy. In terms of just the congestion control, we're all network engineers here in the room, and we want to know if I've got a packet and I'm moving it across the network and I need to make sure it doesn't get lost on the way, I'm not going to send it over by Ethernet, and I'm going to need something else to make sure that my packets get to the place they need to be. without losing them. So what is, I mean, I want to know what's, how do you define state-of-the-art congestion control?
So I would say that it is more recent than DCQCN in this framing, right?
Right.
But we are trying to target over Ethernet, right? We're trying to avoid going off Ethernet. Ethernet has a long history, and that's part of our strategies. Ethernet is the de facto standard that everyone can agree on. So it's got to go over Ethernet. But how you handle loss, how you handle reliability, how you react to loss is a big factor in performance, and that's one of the things that academics have talked about for Rocky for years, right? As an example, right, in the standard Rocky environment, when you lose a packet, you have lots of packets in flight. The general model is, oh, I lost something. I'm going to go back and resend everything. Problem is that that method doesn't work great when you're running a 800 gigabit network, right? So, the first thing most of the academic papers talk about was like, if you look at TCP, it's much better at handling that kind of stuff. There's better retry protocols that exist today. So let's just do that, right? So those kind of techniques factor into Falcon. It's just more recent standard. It's a more recent development. There's things in terms of how you handle, I got some errors, I need to tear down the connection that has software impact. All those kinds of techniques factor in. The spec for Falcon will be available in 24, so that's probably a good, place to go look at some of the things that they're doing inside Falcon. So I'm going to, sort of try and tie everything together. Our belief is that Ethernet is where things are trending and where we need to go, right? At the end of the day, some of these things like the load store semantics on the scale-up network, they're not necessary for these systems, right? They're side effects of other approaches, right? And there is a definite, view that we can get to Ethernet as the baseline for all of these. And Ethernet plus common standards equals a building block approach that will allow us to really tune these platforms. We may not be able to control the power demands of each of these building blocks, but if we can at least figure out more flexible ways of putting them together, right? Because we have the right sort of equal open protocols between them, we'll be able to create different proof points, right? And I think that there's a wider spectrum of needs, right? Not everyone needs the big cluster. The problem is it's a lot of either or right now in terms of what you have, right? And we need to create more fluid solutions along the way. And that's where, our mindset is where we're working towards in terms of our silicon products and our roadmap, in terms of delivering Falcon, in terms of keeping on participating in UEC and supporting UEC when it's available as a wire protocol spec. And that's, I think really our vision for the future of the AI fabric.
Can I ask a quick question there just to clarify from that diagram? So the IPU in this particular use case is headed towards the standard Ethernet data center network because of the ability, the additional management capacity that you have kind of offline from the node. And there's a separate sort of set of specialized infrastructure at the NIC layer that's going towards what you're calling the scale-out network on the back end. I just want to be clear that I was understanding those are two different types of
networks. We still think it's too hard to, there is definitely a different model of serving GPU instances that's actually deployed in Google today, where you just have like a GPU accelerator box that is in the general cloud. But that's much more useful for doing single instances or, a handful of instances at low performance because you're running the interconnect at sort of the more general network with sort of poor congestion controls, worse SLAs when it comes to the overall interconnect. When you're trying to do the really optimized function, you need those tightly connected clusters. And we think that model is still going to stick around.
It reminds me a lot of having fiber channel storage networks and splitting them out, and then we tried converging. Converged network adapters we've all got scars.
Managing quality of service on a broad, hyperscale, million node data center warehouse, and trying to manage that is a hard problem. No one's going to solve that, anytime soon.
Like I could see this going, hey, we go down this dedicated path for a while, and then at some point in the future we go, hey, we'll have all got.
All it takes is one paper that says I can do the same fidelity with a tenth the computation, and the needle moves, right?
So this is It's just funny. It's the same thing. We go through the same cycles, you know?
Yep. It's just it's a lot of similar conversations, just at much higher data rates.
Yeah.
So at the end of the day, Ethernet for scale out is where we think the ball is moving. We want to move there as an industry. We plan to support, robust open protocols. We support Falcon on our Intel IPUs and future Intel Ethernet network adapters. We're working with UEC to create that next-gen AI fabric solution. And we want a healthy ecosystem, right, where AI systems at different scales can compete and innovate. And Ethernet is the way to get there, right? Evolve to a new use case, do it better, do it cheaper. That's what Ethernet has done for 50 years, right? So that's my talk.
One point on there, and maybe we'll talk about it later. I'm not sure, but talk about the working on existing IPUs and just future regular Ethernet adapters like the 900 series or whatever.
That's right.
Guessing what the next version might be.
Yeah.
Pretty close.
But that would, at the Ethernet adapter level, that would be looking at
the
next generation there, because you need the hardware support.
That's right. You can certainly use a IPU on both ends. It's another cost power trade-off calculation, right? So there's arguments for both. If you look at the current proof point, if you look at the reference platform over the last couple of generations, they've sort of oscillated between to put a DPU on that back end or do I put a NIC, right? One school of thought is I want the optimized, NIC because that's the power cost optimized solution. And we certainly hear that from some customers. But there's a perspective that says, well, I'm going to put a DPU there because maybe I can do some other acceleration that is harder to do in a NIC. I think there's a little bit of a dynamic there.
And it's going to change just a little bit, and maybe I've got options with the DPU to do that. But.
Yeah.
I have a quick one. It's Bruno Wallman here. You're talking about these higher speeds and feeds and moving from custom protocols, and there's lots of sensitivity with delays and things like that. You must also be working on something to monitor that to get to, figure out where a delay is in this customized fabric. Or
Absolutely.
Standardized fabric in the future. Like how is that monitored? How do you get to mean time to reduce the mean time to innocence for a certain load or a certain node in the network? Are you working on that at the same time?
That's a great question. So I'll give you a couple anecdotes from our experience building IPUs for the cloud, which is that measurement and metrics are a big factor. Many of these congestion control protocols, for example, rely on highly accurate timestamping, right? You need to know the timestamp at which packets arrive. You need to understand how long are they queued. Some of the academic work in innovations in that space want to look at those metrics at the switches. They want the switches to report those kind of queuing metrics, right, at very fine granularity, because again, at 800 gigabit or 400 gigabit, the latency is very tiny here. So there's a lot of metric gathering. And it's another reason to have that IPU there is that you can't wait for the problem to occur. You need to be doing some element of data gathering and telemetry acquisition in the background to be able to create some context for where the error is occurring before it occurs. Then you can do the next level. But a lot of these, whether it's a NIC or a DPU, having the right measurement mechanics is important at the technology level, being able to understand how long packets take in different parts of the pipeline and the data plane and the different buffer points. And time synchronization primitives are also equally important. At these timescales, the methodologies for doing time synchronization, especially the moment you have to ship a timestamp from box A in a congestion control packet to box B, and that box B has to understand that timestamp, you've created a data center scale timing synchronization problem, which is no wonder a lot of the CSPs are all working on those kind of solutions and how to do, global time sync, right? So
we're finally going to have to start using the PTP features on my.
We support PTP on our product. There are
Look at those
other
little adapters,
right. PTP is one part of
Not
that.
today, PTP.
PTP is one part of that, and it's certainly in use today. There are other things incoming that I think are important. But it gets back to the same point, right?
It almost sounds like you have to have AI to monitor your AI network.
Oh, I'm sure that's already there, right? or it's that's the next VC pitch.
Naru, I've got a question.
Yeah.
So you guys talked about using Falcon to do transport based on Google's input to that. I know that both Cisco and Broadcom have kind of independently come across the idea that using packet spraying and fully scheduled Ethernet is the best way to ensure reliable, immediate delivery with lowest latency. Does Falcon basically remove the need to use packet spraying because it's not reliant upon TCP for the transmission?
Packet spraying is independent of TCP. Packet spraying allows you to use multiple paths in the network. So the Falcon stack does take advantage of that. What you have to worry about with packet spraying is how do you handle out of order, right? This is the classic problem, right? And there are products out there in the switching space that'll do in-network reordering. There are protocols out there that support packet spraying that'll do in-protocol reordering. TCP, for example, can reorder to some level, but it's a code parameter to decide how much reordering you'll tolerate. And in fact, what we find is that the TCP stack in CSP stacks on the back end often tune that parameter because they do a much greater degree of packet spraying, which introduces reordering. And so at the end point, they have a much greater degree of reordering that needs to happen.
So I'll say it, given the hate for TCP that we've seen over the last few years, do you feel like that packet reordering process is going to slowly be moved into hardware, specifically switches for the companies that make those better than anybody else, or some kind of a processing unit for the companies that are focusing on those?
That's a good question. It's certainly capable today, right, to do reordering sort of in NIC, as it were, whether you're doing it on a DPU, whether you're doing it even in a data plane pipeline, right? TCP, much like Ethernet, has also shown, and copper has shown a ability to outlast even the most stalwart competitors, right? So I think it's just another tool in the toolkit, and we have to manage that. With RDMA, out of ordering had some issues. We're fixing that at the protocol level by better support for reordering. Packet spraying at these kind of clusters is a big deal because every stranded wire, every stranded ounce of bandwidth, right, is money lost on the table.